All right. So today I'll be talking about how SSV network is going to scale. But before I'm going to talk about it, I remember 2 years ago in Bogota, in the Devcon in Bogota, we've been running and telling people what is DVT, why it's important, what we're trying to do, trying to share our dreams. And it's crazy to see that in 2 years, so many familiar faces here, and our remarkable adoption, like Alon mentioned before. It's just crazy. It was a crazy journey. And before I'm talking about how SSV network is going to scale really, really soon, let's talk a little bit about what happened in the past year. Our baby is less than 1 year old. It's going to celebrate next month. And it already has around 52,000 validators, 1,100 operators, which is approximately the size of 10% of Ethereum network, which is crazy if you think about it, right? And almost 1.7 million ETH at stake, or already 1.7 million ETH at stake, making us in the top biggest 5 staking platform on Ethereum already. And that's amazing, and it's thank you to all of you who really believe in what we're doing, and we're really passionate about it. So I'm going to deep dive on our core protocol, on our network, and try to share a little bit of how it looks like today, right? So today our network generates around 1,800 messages per second as a whole network. Average operator is subscribed to 63% of them, creating a lot on the operators. It takes to reach a consensus and submit a duty for a validator around 0.9 to 1.3 seconds. SSV's performance, you probably noticed, is one of the top best class performance. Running across the globe, those 1,100 operators, with clusters, with multi-regions, with client diversity. Truly what we thought SSV should look like, and further securing and stabilizing Ethereum. So we started to think about the scale somewhere around the end of last year, and how we're gonna solve problems regarding that. We started with some brainstorming and research. We had a few different type of solutions, and we ended up doing research and simulations, various simulations, until we find a solution which will be resulted in Allen fork, which we're going to discuss in the next few slides. We worked on the implementation. It required a lot of workforce, a lot of effort. We increased our team and passed an audit. And just in September, our testnet forked successfully, giving a great feedback and indication on what to expect happening on mainnet. Today is exactly 2 weeks before mainnet fork. We're really excited about it. So let's understand what it will include, right? So meet Allen, the scalability fork, the first fork on SSV network. It includes a bunch of things, but we're just going to talk about the few core things, changes to expect. One is we changed the way the consensus work. We call it now committee consensus. When we started developing, we were thinking about from a validator perspective. But as the network grew, we saw some patterns, and we will discuss about it and how that is going to change the way SSV works. The second thing is our new network topology. So the committee consensus changing a lot of things, enabling new features, and that also helping us to create a new network, and I'll discuss about it as well. And also a bunch of code optimizations, reducing resources, which we will see in a second. All right, so currently, before Allen fork is happening, today, a validator runs on a cluster of operators. You already know that. So let's take a look on how an attestation duty, for example, is being performed on SSV network today. Attestation duty is at the end voting on the head vote on Ethereum, and you need to sign with your validator key. Validator keys on SSV network are distributed among operators. And so for that, what we call is post-consensus, where each operator submits, sends over the network with his key share, a signature, a partial signature. And at the end, when the threshold met, we can verify and construct a validator's key, a validator signature key, sorry. And then submit it to the beacon node. But as post-consensus suggests, before, operator needs to agree on a consensus on what data they are signing, okay? This process takes around 13 messages that needs to be exchanged over the SSV network, right? And when we think about it, a cluster of operators can run up to 500 validators, and that results in a lot of consensuses, a lot of post-consensuses, and around 6,500 messages per epoch to submit the duties for those 500 validators. And that made us think, right? We brainstormed about it, and we took the data from our mainnet and from our testnets, and we came with this pattern. What you see here is a map of operators and validators connection. So the nodes are representing operators. By the way, that's real data. The nodes represent operators. So as the bigger the node is, the bigger amount of validators it manages. And the edges are the connection between the operators. So the thicker the edge is, they're sharing more validators. And we took this concept, and from there we came with this committee consensus idea. So let's try to understand how it's going to work post-Allen fork, right? So if we take those 4 operators together again, and let's assume they're running 500 validators. On average, they will have 16 duties per slot, right? 500 divided by 32. And if today we did 16 consensuses, right? So at the end, it's a little bit repetitive work, right? Instead of that, what we can do is we can do just one consensus to agree on the same data, and just one post-consensus with batch signatures. Compared to what I showed you before, that's a huge reduction in the amount of messages that the network is going to experience, right? And let's try to look on it. So today it's around 1,800 messages per second. After committee consensus, it goes down by over 80% to around 300. So that's 300 messages per second all over the network to accommodate 50,000 validators. So that's a huge reduction. That's a huge reduction in bandwidth and in CPU time. But that's not just that, right? That's just the committee consensus. That's one part from what Allen fork will introduce. And the second part is the network topology. And let's try to understand how that affects. So if we take in an operator, right, on our SSV network, we use, similar to Ethereum, we use PubSub, we have topics. So SSV network has exactly 128 topics. So if an operator managing one validator, the way we work is we assign deterministically a validator to a topic, okay? So if an operator managing one validator, it will see a fraction of the network, of the network traffic, right? But if that operator managing 500 validators, all right, 500 validators, then the probability that it will be subscribed to most of the topics on the network, meaning it's going to see most of the messages that the network has, right? And creating a load on that operator. So with Allen, we changed the way we subscribe to topics. So instead of deterministically assigning a validator to a topic, we assign a committee, okay? So in this case, if an operator, for example, is in 2 committees running 500 validators, now he's going to be assigned to just 2 topics. So committee consensus reduces those 1,800 messages per second to 300, And the network topology change will reduce that. So out of those 300, you will see only a fraction of that, right? Like just 2 topics from the whole network. And that results in, instead of operators seeing on average 63% of the network, they can see around 2%. And that's a reduction of 96% of the network that they're going to see. Those 2 things together reduce significantly and allowing scale for SSV network to keep growing like we anticipate. So if I'm summarizing the effects of LN fork, we're going to be reduced to around 300 messages per second. Operators will see much less messages while keep doing the same duties and keep being a transparent network that brings so much value to everyone in this ecosystem, where we can see in a transparent way everything what's happening. Everybody can know like the performance of their operators, or stakers can see the performance of the operators that they use. And the consensus time is expected to be reduced significantly. So if today we are around 1 second, 1.3 seconds, we're expecting to see it around 1.1 to 1.4. That means faster votes and maximizing rewards for validators. We are being very conservative about CPU reduction, that it will be at least by half reduced, and we're really excited about it. And about around 90% of the bandwidth that currently required for an operator to run on SSV network. And it's naturally aligned, because we always try to be aligned to Ethereum, and that's why it's great, because that's what makes it easy, right? Like when Pectra is coming for Ethereum, to scale Ethereum, it scales also SSV, right? Because we expected to see a consolidation of validators, meaning less validators on the network, even further reducing the amount of messages while the staked ETH will increase. So be prepared. First, 25th of November, 2 weeks from now, the fork is happening. Operators that are here, please upgrade your operators. We released the new version already. Do it as soon as possible. Don't wait for the last minute. And for the last thing I want to say is that LN fork is not just a scalable fork for the SSV network, but rather it allows us for the next year. Alon said we're going to talk about next year. We have a very heavy and interesting roadmap for SSV network in terms of the core protocol changes and optimizations. And one of them is, I know that a lot of operators asked for it. So today, operator is limited for 500 validators, and we are exploring increasing that for 1,000. And what's interesting is that if before LN fork today, that will mean that it will grow linearly, right? Like you'll have twice of the consensus to do as an operator. But as we talked, that wouldn't affect too much on the network, right? Because if instead of 16 validators per slot on average, you will have 32, but the consensus will be the same, right? So this is just one piece of what this scalable change is going to bring for us. Thank you very much. So excited that you're here.